Welcome to the session again. So here we're going to discuss about building the architecture of speed. That is about how the catching and all works and all. So here we're going to discuss how the data retrieval or fetching of the data could be made much more efficient and much more easy. So you could see the line defeating distance and disk mechanics with Redis and in-memory systems. Please move ahead on. Yeah. So we're gonna discuss how the computation could be made fast and what are the main equipments required over there and how does it go and all. So computation is fast. Fetching data is a bottleneck, right? Fetching data is much more important where you're utilizing some applications, might be other web applications or even uh, mobile applications. At last, in order to fetch the data, we have to go through the CPU, cache, or RAM, or it might be SSD drive or HDD drive or any network database. But try to understand if a data has to be fetched from the database or any data storage, kind of CPU, cache, RAM, and all, you have to consider what is the easiest way. What makes the data fetching to be very simple and very fast. So you could see the comparison between the different sources, in what ways or in what amount of time the data could be fetched and retrieved. So there comes the CPU cache in the first place, and then the RAM, and then the SSD drive and HDD drive and network database. Please move ahead, Pawan. Diffusing distance, the library analogy. Without cache and with cache. So while we are talking about catching so far, here also we're gonna discuss and differentiate what makes the difference without having any cache and with cache actually. So try to understand if there is some person upon the 10th floor and he has to reach the ground floor, which is the destination. There are multiple ways for him to reach the destination, that is the ground floor. But it depends on the ways he chooses. Like suppose he has an elevator to choose and to reach the destination. He might have a lift. He might have some stairs in order to walk down, right? So there are different ways of getting to the destination, but definitely you'll be choosing the most easiest way and uh, way more better way, right? So in that sense, in a technical way, every request queries the database. The system does the heavy lifting every time, but here catching plays a main role in order to solve this issue. And also an example that suppose there is a librarian and there is a student coming up to the librarian, right? And the student asks for a certain book, right? And the librarian has to search for the book. Might be the book is all messed up in the complete entire library, a big library, and it may also be that the books are existing on the table, right? So it's better and much more easy when the popular books or the required books are available on the table, and it makes the librarian to pick them up directly and easily. So future request read directly from memory. The most popular data is immediately accessible in that way. Please move ahead, Pawan. Bypassing the disk with Redis. So what is Redis? Redis is a way or it's a source through which the data catching, that is also fetching the data, could be made much more easier. Kind of web sessions, AI embeddings, gaming, and mobile APIs. These are the scenarios where Redis could be very helpful. You could also see direct memory access. So it stores the data entirely in the RAM. So that picking the data, fetching the data is made so simpler. And also you could find the time complexity big O of one operations. So it is highly optimized algorithmic speed. Also you might understand with the event loop, which is single threaded design that avoids locking, and it provides microsecond latency. That is, it is very fast. The delay is very low actually. So it bypasses disk input output completely. Please go ahead, Pawan. The mechanics of a request, hits and misses. There's a scenario where the data is stored in the RAM, and if something has to be, the data has to be fetched out, right? And it is possible only if the data actually exists in the RAM. In the same way, cache hit is something where if the data exists in the memory, then it could be returned immediately. So cache hit does that. If the data is existing, then it could be returned. It is explained in this scenario. And the second scenario is that having no data in the cache, and the data could be fetched from the database and then stored in the cache, and then the retrieval is made from the cache. That is, if there is no data in the cache, then first request is sent to the database. That is way slower than the request sent to the cache because it is more distant, right? The first request gets low, and the next request, which will be fetched from the cache, will be made faster. So data is fetched from the database, stored in the cache, making all future requests very fast. Please move ahead, Pawan. Matching data structures, application needs. So for certain kind of tasks that we are applying in our regular days, there are certain types of methods. So there are definitely types of methods that we are using for types of tasks. In the same way, Redis is an in-memory data structure server, not just a simple key value store. So it utilizes different data structures for different services. Here you might see the different data structures are strings, list, access, sorted, and they have different purposes and way of utilizations. Where you could find strings, simple key value pairs for user sessions and caption. For the list, ordered collections for background job queues. And the next, sets, unique unordered values for unique visitors and tags. The next, hashes, objects with mapped fields for user profiles. And then sorted sets, values ordered by a dynamic score for gaming leaderboards. In a similar way, we'll move ahead. Strategic pathways for data movement. It might also be considered for data transfer or data to be traveled. In what ways it might be? Again, there are three types of methodologies: catch aside, write through, write back. You might look into the pictures that in the first one, catch aside, while an input is sent to the application or a request is made from the front end, then the app might directly reach out to the cache or might also travel to the database and then reach out to the cache. Might be direct or indirect. So it is industry default. App auto-saves between database and cache, which is simple and efficient. But the first request is always slow. And next, going to the write through, the app might move directly to the cache or directly through the database. So app writes to cache and database simultaneously. Cache is always updated, but write operations take slightly longer. And then moving to write back. The app might directly reach out to cache and then from cache to the database, consuming some time. So app writes only to RAM. Async, sync to database later. Lightning fast writes, but carries a risk of data loss. We'll move ahead to the next slide. Managing finite memory, expiration, and eviction. Now, let's understand what do you mean by finite memory. You could also recall the two words finite and infinite. What exactly do we mean by infinite? Something that is no longer ending at all, not at all ending, right? That is infinite. And finite is somewhere somehow limited, right? So we are going to discuss about managing finite memory in the slide through two methodologies again. The first one is expiration, which is describing about time factor, and the second one, eviction, which is describing about time space factor. Right? As we heard, there are two types of complexities: time complexity and space complexity. In the same way, here we'll find expiration and eviction similar upon time and space. Right? So expiration is depending on the time factor. Right? Whether if a request is sent and some data is stored, the data would be stored based on time factor. Like you might look at the TTL, that is time to live. It decides how much time a data should be relying or staying upon the RAM or cache, right? And if the time expires, then the data would be directly kicked off from the cache. And coming to eviction, eviction describes if the space is already occupied and there is no more new space available, right? Then the space is made through kicking out the existing data and making space for the new data coming in, right? So there are some rules and regulations, also termed as policies, which has to be considered in order to perform eviction. Those are LRU, least recently used, pushes out oldest unread data. And next, LFU, least frequently used, pushes out least popular data. And then come into FIFO, first in, first out. And then come into random, that is random removal. A cache that never forgets becomes a memory leak. We'll move ahead to the next slide. Pawan, could you please? Yeah. The invalidation paradox, the danger of stale data. Now, what do I exactly mean by stale? Right. Something which is of no use or something which has already satisfied its perspective or objective in the sense of technology, right? Stale is something which has satisfied its objective or perspective and now holding no value. It could be termed as. So cache invalidation is notoriously difficult in distributed systems, right? If the database updates, the cache must be explicitly purged. Where purged in it means deletion, could be explicitly deleted. Now, in order to handle all of these, there are some solutions again which could be implemented. Implement short TTLs. What do we mean by TTLs again? Let's recall to the previous slide. TTL in the sense time to live, right? TTLs and event-driven update architectures. You could also recognize what matter is exactly conveyed here through the image presented. We'll move ahead with the next slide. Pawan, could you please move forward? Yeah. Breaking the single node limit with clusters, right? Now, it might depend on how many nodes we are utilizing, right? You might also understand in a laptop what you are using, right? It exists or it depends upon how many nodes or it is also kind of yeah, it's somewhat around nodes, right? So breaking the single node limit with clusters. We shall discuss if there is huge traffic or huge data coming in, then how it could be handled. There are two ways: horizontal scaling and vertical scaling, right? The first one is data sharding. Memory is mathematically partitioned across nodes. Second one, limitless scale, breaks the physical hardware limits of a single machine. The third one, high availability, built-in fault tolerance if a single node fails. Right. These all have to be considered for understanding how the data is stored within clusters. Is it single node or multiple nodes or through vertical scaling or through horizontal scaling? We shall move ahead. Ensuring resilience in volatile memory. right? Resilience in the sense staying for a long duration, how resilient it is, right? So we're going to discuss about disk persistence, replicas. Now, what do we mean by replicas? Replicas of, replicas are duplicates, to be explained in simple words, right? Replicas provide constant backups, right? Suppose if we have multiple copies of data, then even if one copy is lost, we will have a few more copies in our backup, right? So replicas provide constant backups. If the master burns down, Sentinel automatically promotes a replica, right? Replicas provide constant backups. If the master burns down to disk, you could also see it is conveyed through certain images here, right? Yeah, moving ahead. Distinction between edge delivery from backend memory. Now we have CDN, that is content delivery network, and also in-memory cache, that is Redis. Now, trying to understand what is the difference between them, the first point, what we have here, edge geography. Geography in the sense, location, right? Location where it exists or location where it could be accessed. That is global content delivery. Whereas in-memory cache, it is local application data caching. And coming to asset type, it stores static files. And coming to in-memory cache, it stores dynamic database results, JSON, and session states. Now coming to location again, some more supervised or improvised, lives on edge servers physically close to the user's location. And coming to the location in memory cache, lives in backend memory directly next to the API and database. So a CDM defeats physical distance for static assets, Redis defeats mechanical disk latency for dynamic data. Moving ahead, the big picture, modern prediction architecture. So what is the exact architecture utilized here? Let's try to understand that. You could also go through the image for understanding the architecture, or in another sense, we can try to understand that once user traffic is attained or achieved, it goes to the API gateway, and then it might get into the primary database or even Redis cluster. And then if it goes to a Redis cluster, it goes to the backend or background worker nodes so as to distribute. So continuously pulling from Redis messaging queues. Now, let's try to understand where this architecture is mainly applied in the real world. We can call Netflix, Uber, Discord, GitHub, and X, that is Twitter, where this is applied. So Redis operates as a performance engine of the entire stack, not just as a simple cache. Let's move ahead. Avoiding common implementation traps or avoiding making simple mistakes, right? Catching everything. RAM is a premium expensive asset, right? Storing rarely access data waste memory. Only cache what is frequently read. So RAM is something existing very close to the front end or in order to fetch the data, right? Catching everything. And then missing TTLs. Now let's try to recall what is TTLs again. That is time to live, right? Missing TTLs. Failing to set a time to live on cache data creates an inevitable memory leak and serves permanently stale data to users. Coming to cache thrashing, constant cache misses caused by poor invalidation logic. The system spends more time updating the cache than serving fast reads. Coming to distributed complexity, what might be the concept here? Underestimating the difficulty of multi-node coordination, a poorly configured cluster can lead to split brain scenarios and data loss. Let's move ahead, getting to know much more about this. The 60-second blueprint for system speed. So far, we're gonna make a final overview of what we've discussed. Redis. That is, in-memory engine utilized for bypassing mechanical disk 1 by 0 or I by O. Then catchy hit or catchy miss based on request flow that acts on the dividend. Coming to TTL, automated expiration, preventing stale data. Eviction, space management, LRU or LFU, dropping bold data. Cluster, limitless scale, sharding memory across nodes. Persistence, crash safety, RDB snapshots, and AOF logs. Databases are built for long-term truth. Redis is built for high-speed access, master caching, and a master scalable system design.